And yeah, welcome again for the afternoon session today. So we have again 3 exciting talks. The first speaker is Nicole Immorlica. She's a senior principal researcher at Microsoft Research New England, where she leads the Economics and Computational group. She received her degrees from MIT in theoretical computer science, and then she spent some time at Microsoft in New England as well as CWI, and thereafter Northwestern before returning to Microsoft. Her research interests are in design and operation of sociotechnical systems, and where she uses tools of modeling and concepts from both theoretical computer science and economics. She's received multiple awards, including the Sloan Fellowship, Microsoft Faculty Fellowship, NSF CAREER Award. And she's been on several boards, including SIGACT, Game Theory Society, and OneChronos. Anyway, with this, I give this.
Thank you. So today I want to talk about a sort of high-level agenda that I have in mind for what I think is an interesting direction for future research, and I call that data the fundamental particle of economics. So what I'd like us to contemplate is to think about data as really the driver of all economic models, and beliefs, priors, posteriors as just sort of derived from data sets. So as you probably know, most of classic economics is built on this idea of a prior. Agents hold in their mind some probability distribution over a state of the world, and then they choose actions based on this probability distribution in a way that's going to optimize their utility. But one thing that is quite apparent in the world, especially today with the growth of access to data, is that a lot of decisions are made by looking at data. So this, for example, is a spreadsheet from the EU ETS about the emissions license and pollution of various companies. And the EU ETS will use information like this to figure out how many emission licenses it wants to auction off every year. And I can't, of course, show you internal data at Microsoft, but everything we do, we have massive amounts of storage devoted to maintaining data sets that are going to inform future policies, allow us to make conclusions about the world and how to, use those conclusions to change what we implement. And it's not just companies that act like this. I think human beings also leverage data in deciding how to act. And I'm going to start thinking about data as anecdotes. So what is an anecdote? It's a true, immutable story that was generated by nature. And here's an example of an anecdote. I gave a talk at HGI in Stockholm, and I went around, the day after my talk to look at the city. I wanted to get a coffee. I went to the photographics museum and had a delicious coffee on the deck overlooking this beautiful water with a little yogurt. The table next to me, there were some dogs, which were very adorable. And so, this is what I have stored in my memory as an anecdote. And when people are going to ask me about how is the coffee in Stockholm or like various other such questions, I'm going to reference this anecdote, think about it, and come up with an answer at that moment. It's not that I'm storing some model in my head of some probability distribution over the quality of coffee in Stockholm. And something to notice about this anecdote that I've told you is that it has many features. I talked about the coffee. I thought about the yogurt that I'm eating with the coffee, which was healthy. I noticed the view. I noticed the dogs that were at the table next to me. And so, this is a story, and it's also a high-dimensional story. And I'm going to leverage both of those features in thinking about how anecdotes impact behavior. So why, you might think, if I want to answer questions about the quality of coffee in Stockholm, I'd be much better off fitting some model of coffee quality and talking to you about that model. So why are we why do we remember anecdotes, and why do we talk to each other by telling each other anecdotes? And I think there's two sort of driving reasons for this. One is that anecdotes are particularly useful for answering questions when you don't know what the question will be. Okay, so if I knew that you were going to test me on the quality of coffee in Stockholm, I might have just done some fit of some model I have about quality and coffee and stored that in my memory, right? But if I didn't know that you were going to ask me about coffee in Stockholm, or maybe you're not even going to ask me about the coffee. Maybe you're going to ask me how dog-friendly is Stockholm, right? It's much more useful if I have all this raw data in my head, and then I can answer questions on a dimension that I didn't know I'd be asked about. And so that's, I think, one reason that you could imagine storing anecdotes in your memory is useful. And another reason is that I also kind of lack the expertise to store anything other than anecdotes, right? It's not like I work for the Michelin Guide and have a very well-formed model of how an experience at a restaurant relates to a star rating, right? I instead have some sort of vague feelings about it. And that's in essence because I'm not an expert in restaurant qualities, right? So I think when agents lack expertise, they might be better off thinking about experiences that they've had and keeping track of those than trying to fit some model because they don't even know the model. And then that additionally leads to this observation that if I am not an expert, or even if I am an expert, but I want to tell a non-expert something about what's happened to me, then the non-expert doesn't share the same language as I do, right? So I can't talk to them in terms of, I don't know, elasticity of demand. Instead, I'll just be like, wow, the line for bread was really long, right? You can't talk about things that your listener doesn't have the same model as you. And so talking about anecdotes is sort of a more common language in which we can all communicate. So this is kind of the high-level motivation for my model. Yes? So by anecdotes, I mean there's going to be some state of the world. And so, I kind of mean at an intuitive level, stories about what has happened to you. But in a modeling sense, what I'm going to say is there's some state of the world. And anecdotes are, this could be high dimensional. Throughout the talk, I'll consider it to be single dimensional until the very end. But then anecdotes are simply going to be samples drawn from a distribution that is parameterized by the state of the world. You should be thinking about this as the state of the world plus Gaussian noise or Laplacian noise. And so those are anecdotes. And now what I want to think about is how does access to anecdotes and basing decisions on anecdotes impact economics? And I'm going to look at this in the context of three sort of classic areas of economics: decision theory, communication and persuasion, and mechanism and information design. So in each of these areas, there's been several papers thinking about this kind of stuff before. In decision theory, there's some beautiful work thinking about how agents use case-based modeling to come up with assumptions about the world and how that impacts their actions. In communication and persuasion, there's a literature on sort of hard evidence, which you could think about as a type of anecdote, and how agents can leverage hard evidence to try to convince others to take particular actions. In information and mechanism design, there's a long line of literature in the computer science community thinking about how to design mechanisms when you have samples from types. This isn't exactly what I have in mind. That's why those papers are in gray. But there's also more recent work thinking about mechanism and information design when that's part of the language with which the agents communicate to the principal. And so I'm going to talk about 3 papers that I've worked on in this line of literature. And I guess sort of at a high level, what I think we learn by taking this perspective is, first of all, we understand better principles that are maybe more robust and more transparent to the settings at hand when we take seriously the idea that agents are leveraging data to do stuff. And it also allows us to make some observations about the outcome space that might not be apparent if we think about agents passing around priors or acting on the basis of rich priors, things like herding and bias and polarization. So let me start with the decision theory paper. And so this is joint work with James, who's here today, and also has a poster on this topic. If you want to hear more, or maybe you already heard more yesterday, you can approach James in the poster session. And so in this paper, we ask if agents have limited memory, and they're going to sort of take actions on the basis of what they can figure out about the state of the world given their limited memory, then how much memory do they need to be pretty accurate in what they believe about the world? And what we'll see is that you only need, logarithmic memory if you can strategically forget certain stories. And what we'll see is that this is a sort of reminiscent of the confirmation bias, that people are more likely to remember things that confirm their current beliefs in the algorithm we come up with for the agent here. So let me jump into that. I'm going to ask, how do agents make decisions, and how good are the decisions that they make when they're leveraging data to make their decisions? And I'm going to do this in the context of a specific model. So I have anecdotes that arrive over time. And so on day I, anecdote, or day T, anecdote ST arrives. And then the agent has a memory, which at any point in time is a collection of anecdotes that have arrived in the past. The agent can, when the anecdote arrives, the agent can remember that anecdote or forget it forever. And then at some point T of the agent's choosing, the agent is going to guess what the state of the world is. So throughout here, I'm assuming that the mean of the state is what matters to the agent. So at some time T, the agent is going to stop and make an estimate as to the state theta. And importantly, this estimate must be a function of the collection of anecdotes that are in the memory at that time. So what I want to understand is how good of an estimate can an agent generate? And I'm going to judge this based on how close the agent can guarantee they are to the true state at time t. So the agent wants to pick a time t that's as small as possible, that satisfies that it's with high confidence, high accuracy, right? So with high confidence, with probability at least 1 minus delta, the agent wants to pick a capital T such that the guess is is within epsilon of the true state. Yeah, good. So I'm going to assume memory is unordered, so you don't have timestamps with your anecdotes. It's a set of things that you've observed in the past, and it's the story itself. It's not when it happened to you. Yes, this is definitely restrictive. You can't just take averages over time because. So what we like to think about is if you had this unknown unknowns setting, right? Like here, there's only one dimension, so you know what question you're going to be asked. If you had mean and variance, maybe you wouldn't know which moment of the distribution you're going to be asked about. We're actually instead thinking about the anecdotes as being high dimensional, and there's some basis that's in which all questions are asked, and so, but you don't know the basis, and so, but that's a good sort of thing to try and compare to is like if you had perfect memory or if you could take averages over time, how long would you want to wait in order to get this kind of quality guarantee? And so, yeah, so that's the question that I'm going to introduce now, which is like, if the agent had perfect memory, then they, or they could take averages, then they would just want to weight something like 1 over epsilon squared steps to get an estimate that's close to the true mean, and that's going to be by the central limit theorem, and you can also show that you can't do better than that. So with perfect memory, you need to weight something like 1 over epsilon squared steps until you can make a guess. But what if you have bounded memory? So I haven't yet introduced this idea, but clearly I'm leading up to the idea that we can't remember everything that happened to us in great detail. So what if you had a bounded memory of size 2? Could you still do well in terms of this getting good estimates quickly when you just can remember 2 things? And I think the intuition might be like, well, sort of the naive thing to do would be to remember the most recent things that happened to you. So let's just always remember the last 2 things that happened to you. And is that going to do well? Well, that's basically a random sample of size 2, and so it's going to be super noisy, right? And so that's not going to do well. So what you have to do instead is figure out what you're going to remember and what you're going to forget. And so we call this strategic forgetting. And what I'll show you in this portion of the talk is that if you can strategically choose what to forget, then you can actually get quite close to the bound of that you could get with perfect memory. So you can get a t on the order of 1 over epsilon squared. Yes?
Can't you just take the average memory?
So I'm not allowing you to, so you shouldn't think about this as a computer scientist as like you have a bit, some number of bits in your memory and you can do anything you want with them. I'm only allowing you to store stories. So you can't take averages. You only get to take the average when you're asked for your guess. So yeah, I didn't want to go into this high dimensional setting. I just want to study this question. But like, if you have a high dimensional setting, if you know the base, like let's say that every point lies in a d-dimensional, like it has d dimensions, but it lies in a d star dimensional space for some d star that's much less than d, and you knew which, like a basis of this space, then you could just play this game on every component of the basis. But if you don't know the basis, then you might want to try to remember enough dimensions that you can, and so this is like very current work. This is where we're trying to go with this, but we haven't gone there yet. But this is going to be like the workhorse underlying that model. Yeah?
Did you make any distributional assumptions?
I am. I kind of swept that under the rug. Theta, I'm assuming, is drawn from a diffuse prior. The noise is going to be single peaked, like and symmetric. So like, say, the anecdotes are Gaussian with mean theta and variance 1 or something. The fact that what? Mean and median are identical? No. Okay, so let me show you how to do better with just 2 anecdotes. I think this is, with just memory size 2. So what you can do, you have your same problem set up as before. Anecdotes are coming 1 at a time. You have 2 slots in your memory. You get to decide what to put in there. And you're going to divide the memory in half. You're going to call 1 half the short-term memory and 1 half the long-term memory. And now what happens is so now I slightly lied to you before for the sake of clarity, which was that like I'm allowing you to do this minimal amount of ordering in the memory. So when there's two memories, you can think about this as remembering which one was earlier. And so now I'll show you how you can like store stuff in the short and long-term memory, and then when you decide to make a guess, you're going to say that your guess is the anecdote in the long-term memory. So how can you do this? What you want to do is you have something in the, like, on the first day, you just put your anecdote in your long-term memory. It's the first time you've ever experienced this thing. You just remember what you experienced. And then in future days, in the second day, let's say you put the thing in your short-term memory. So in future days, you're going to have something in the long-term memory, something in the short-term memory, and an incoming anecdote. And what you look at is the short-term memory and the incoming anecdote both on the same side of the long-term memory. So I'm thinking about all of this as living on the real number line. If they're both x and s are to the left of y, what it means is that you now have two experiences that are pulling you towards the left, suggesting that maybe y is too far to the right. And so what you would like to do is move your y, which is your estimate of the state of the world, more towards the left, more towards the side that contains both x and s. And so what you might want to do is, okay, I should change my long-term memory to equal something on the left, say st, the incoming anecdote. And this would be great, except you also, if you just do this, whenever you have two anecdotes on the same side of the long-term memory, then you might jump around a lot. And you want to make sure that you're close to theta at the end, so you don't want to take really big steps. You don't want to change too drastically. And that's what I see as sort of an evidence of confirmation bias in this model. You're trying to update your memory. You're willing to learn. You're changing what you feel, what you think about the world based on your experiences in it, but not very drastically, right? You don't want to move too far. And here's some plots that James generated, sort of showing what happens based on how fast you're going to move around. So here, psi, is that the name of that Greek letter, is very tiny in this simulation. And you can see the curves here are the distribution of the anecdote in the long-term memory after a certain number of steps. So at t equals 1, it's just the distribution of the anecdotes. It's blue. It's underneath all these other curves, so you can't see it. And we ran the simulation for 1, 2, 10, and 20 steps. And what you'll see is that because the step size is so small, you aren't ever really getting anywhere. The distribution of what's in your long-term memory stays pretty much the same. Because you're never finding something that you can remember that's close to what you already believe, right? Now, you could also say, okay, so you're learning something, but super, super slowly. What you should do is be a little bit more open-minded and allow yourself to remember, like, store memories that are quite far from your current belief. And so you can do that. Here's the same simulation, but with a much more permissive belief system. This is letting you store anecdotes that are a distance of 2 from your current belief. And now what you see is that the distribution of what's in your long-term memory has converged fairly quickly after the yellow and purple curve are basically on top of each other here. That's because after 10 steps, you've basically converged to a distribution of what's in your long-term memory, but it's not very tightly concentrated around 0, which is theta. It's not very tightly concentrated around the state of the world, and that's because you're just constantly overshooting it, because you're too open-minded. So you're jumping around in the state space quite a lot. And so there's going to be some sweet spot where you are learning quickly enough, and that's what's happening in this simulation, but at the same time, your step sizes, so your step size is large enough that you're learning quickly enough, and your step size is small enough that once you've gotten close to theta, you stay close to theta. And so I think that these pictures sort of illustrate the idea. You can turn this idea into a proof and show that if you weight just something like 1 over, I think our current proof shows epsilon to the 16th. I didn't want to write down a specific p here because I don't think that's very optimized. But we have a proof that you can show 1 over some epsilon to the p is going to suffice as a waiting time until you know that you're in close to the state, and then you can make your guess. And the proof technique, or the proof sketch here is I think, intuitive given the pictures I just showed you. We'll interpret what's in your long-term memory as the state of a biased random walk. And now from the start, you might be very far from theta, but because I've assumed that my noise distribution is single peaked, my random walk is going to be biased towards theta. And so you can show that if your step size is permissive enough, you're open-minded enough, you won't spend too much time, you're always drifting towards the peak of the distribution, and you won't have to spend too much time to get inside that epsilon confidence bound that you're aiming for. And then the second step of the proof is, okay, now let's imagine that you're inside that epsilon confidence bound. If your step size is small enough, then you're not going to leave it too often. And therefore, with high probability, when you stop, you'll have a memory that's close to the truth. And so it's just, there's some math to work out to make sure that there's something that's large enough and not too large, right? And so that shows you that you can actually do something non-trivial with even just 2 memory states. But recall that when you have perfect memory, you can learn in just 1 over epsilon squared steps, right? You could decide to make a guess after just 1 over epsilon squared steps. And what I showed you is something like 1 over epsilon to the p. And we actually know, we have a proof that with constant size memory, you can't get 1 over epsilon squared. So you might ask, are you really sacrificing anything through this anecdote thing? And what we show is that if you have sufficient memory, something like logarithmic in 1 over epsilon, then you can get the same, you can learn as quickly as somebody with perfect memory. So I guess this is kind of a answer to Kamesh that you really wanted me to take averages and I refused to, but I'm not losing anything by refusing to take averages so long as I have sufficient memory. And this, really what's driving this result is in the 2 memory case, I had to take small steps, or steps that at least weren't too large, right? So I might have to wait a really long time to find an anecdote that's close enough to my current long-term memory for me to decide to store it. But when I have a memory of size m, then there's sort of 2 to the m choices of what subset of things I can choose to remember. And so I'm going to leverage these 2 to the m choices of what subset I can choose to remember to find a step size, to find a set of them that averages to a small enough step and remember those. Right, so I'm not going to go into that, but if you're interested in the details of that algorithm, James will be at the poster today from 5 to 7, and I encourage you to check it out. Instead, what I would like to do is move on to the poster that my second postdoc here is presenting, which is Divya, who's sitting also in the audience, on communication and persuasion. So this is a model. I actually talked about this in one of the virtual colloquia of this consortium, so some of you may have seen this before, but here I want to say, okay, we've seen how agents act if they can just, what we can do as a single decision maker if I can only remember anecdotes. What about if I can only communicate anecdotes? So now I'm not a single decision maker, I'm I'm in a world with one other person, and I want to decide what to tell them about. I have access as a sender to a set of many anecdotes, and I'm going to cherry pick what I talk about, what I tweet about on social media, and which ones am I going to choose to talk about. And so what we show in this paper is that when you have anecdotes that are noisy and biased, when you have misaligned preferences, the anecdotes that you choose to talk about are going to be out in the tail of the distribution. They're going to be noisy and they're going to be biased, and therefore this is going to give, I'll show you, gives a force towards polarization in society, because you would rather talk to somebody whose preferences are aligned with yours because they'll send you less biased anecdotes. So here's the model. We have a sender who's talking about the state of the world, and we have a receiver. So the sender is going to be informed. The sender has access to lots of anecdotes. The receiver is uninformed and listens to what the sender says and then decides to take an action. And the sort of driving force here that makes this game interesting is that the sender's preferred action might be different from the receiver's preferred action. So maybe the sender, if the state of the world is theta, the sender wants the receiver to take an action that's far to the left of theta. You know, I am, say, like, have a lot of information about COVID, and I know that mask wearing is effective, that's the state of the world, and I want people to wear masks like 100% of the time. But the receiver, even if they knew exactly how effective mask wearing was, has maybe stronger preferences than me for personal freedoms, and therefore would want to wear masks only 75% of the time. So the sender and receiver are going to have potentially differing personal biases. And the sender is going to observe anecdotes and pick one to communicate to the receiver. The receiver is then going to take an action, and this action generates a payoff for both the sender and the receiver, which is the distance from the action that the receiver took to that corresponding agent's preferred action. Okay, so the action is payoff relevant for both the sender and the receiver. Then we can ask about the perfect Bayesian equilibrium here, which is just some sort of, so this is like a cheap talk game, like Crawford-Sobel, if you know that paper, right? Like, so I'm looking at the perfect Bayesian equilibrium. There's no commitment. The sender can't like commit to their signaling scheme up front. They're best responding to the receiver, how the receiver is going to react to what they say. And so in this kind of equilibria, you can ask what types of anecdotes get sent and what types of actions, like how does the receiver act based on the anecdotes that are sent, yeah?
MS and NE are commonly known.
Yes, the biases of the sender and receiver are known. The bias of the sender needs to be known. I'm thinking about things like the New York Times is leftish. The bias of the receiver, it could be drawn from a distribution, and you can take MR to be the mean of that. Am I allowed what? No, you have to send an anecdote. So in Crawford-Sobel, sorry for those that don't know the model, the result is, the setup is exactly what I've shown you, except for the anecdote thing. And the result is that the sender will choose there will be a coarsening of the state space, and the sender will tell the receiver in which partition of the state space theta lies. And they describe this as, if we aren't very aligned, our preferences aren't very aligned, we kind of, we can say things to each other that aren't just complete babbling, but these things are kind of vague. And our result, whatever you say, has to be an anecdote, so you can't just give an arbitrary partition of the state space. But I'll tell you what that anecdote looks like as a result. So the equilibrium is going to consist of how does the sender pick the anecdote and how does the receiver respond to that. So I'll define a class of schemes I call targeting schemes. And a targeting scheme is going to select the sender. This is a communication scheme for the sender. The sender picks some sort of representative or some sort of target, like some sort of anecdote that they would like to tell the receiver, which might be, if their preferences are to the left of the receivers, maybe their preferred thing to send will be to the left of the state of the world. And now I'm insisting that the sender can only tell an anecdote. So she can't send just theta plus tau. She has to send an anecdote. So she's going to send the anecdote that is closest to her target, the starred one in this case. And this is the targeting scheme. And the bias, it's going to have some bias, right? So the bias being how far is the anecdote that she sends from the state of the world. That's what I'm defining to be the bias of this scheme. It's going to be something that's, because this distribution is single peaked, the anecdote is going to be to the right of the target, right? It's like the bias is going to be a bit smaller than the target because there's more anecdotes to the right than to the left. So the bias will be something like there on my picture. And one thing that really drives the equilibrium characterization that I'm going to state is this gap between the target, the left blue line, and the bias, the right blue line. So one thing to note is that there's going to be, unless you're targeting theta directly, there's going to be some distance between the target and the bias. So that's the class of action rule, the communication schemes that the sender will use in the equilibrium I'm going to derive. And now let's think about the class of action rules that the receiver will use in the equilibrium that I'm deriving. So they're going to be translations. And why is that? Well, the receiver knows that the anecdote they're getting is biased. You know when you read the New York Times that it's a bit leftist. And so what do? You think, well, I want to debias it. And so you take the story that you're told and you form a posterior about the state of the world, which is, remember, my theta is drawn from a diffuse prior, so my posterior is just going to be that anecdote shifted back by its bias, by the bias of the scheme. So if the starred is the anecdote that's sent and the bias of the scheme of the sender was some beta, then the receiver is going to form a posterior, which is take the star and shift it by beta. And then the receiver's preference for the action that she wants to take is shifted by an additional MR, so she's going to also add in that shift, and that'll be the action rule that she selects. So the action rule is just take the anecdote that was sent and shift it. And now I can tell you the equilibrium characterization, which will allow us to make conclusions about the sort of economically meaningful conclusions and comparative statics about how people behave in this world. And so the equilibrium characterization says that the targeting, like a strategy profile is an equilibrium in the broad set of everything that people can do, if and only if this gap that I was telling you of between the tau, the target of the communication scheme, and the bias of the communication scheme is equal to the preference misalignment. And then the action rule does the appropriate debiasing. Okay, so these are what this is always going to be an equilibrium. And here's what it looks like pictorially. In my picture has some gap between the ideal actions of the sender and the receiver. That gap, what I, as the sender, need to do is to find, I could think about starting around, what if I try to find the anecdote closest to theta? Well, that might be that's going to have a zero gap between the target and the bias, right? That's unbiased. So now let me try dragging my target to the left. As I drag it to the left, the anecdotes get thinner and thinner because the distribution is single peaked. And so the gap between the target and the bias grows. And at some point, I will find a gap between the target and the bias that equals the preference misalignment. So this, I'm not going to prove this theorem for you. We derive some best response functions. You can look at it in the paper. What I think is more interesting here is that there's some comparative statics that fall out of this characterization that I find pretty fascinating. So let's look at that formula, right? We know that this preference misalignment should equal this gap between the target and the bias. So if we fix the number of anecdotes that are available to the sender, as I have throughout the talk so far, then one thing to notice is that as the preference misalignment grows, right? If I'm the New York Times speaking to a society that's very far to the right of where I am, then as that difference grows, as we become more and more misaligned, I, as the sender, am going to pick anecdotes that are more and more out in the tail, because I need to find a target that's far enough out in the tail that it's the difference between the target and the bias equals this MS minus MR. Okay, so I think that's pretty clear, and that's also a conclusion that exists in prior work, that, you know, as people are more misaligned, they have a hard, like, this is bad, by the way, because things out in the tail are noisy. And so this is also in prior work, such as Crawford-Sobel, that like when we're misaligned, we have trouble communicating accurately, right? The other thing that I think is cool is that let's now fix the preference misalignment. So I'm fixing the right-hand side of my equality. And let's consider two different senders. So this is like a hypothetical world. There's two different senders, and one has way more expertise than the other. By that, I mean one has way more access to way more anecdotes. They've been around in the world for longer. They've collected way more anecdotes. So you might ask, which sender would the receiver rather listen to? The one that has more experience, or the one that has less experience but has a better, like, has preferences that are more closely aligned with her own? And what you can see from this equality is that as the number of anecdotes grows, the sender has to go farther and farther out in the tail to get this equality, because the anecdotes are now more dense everywhere, right? So I have to go farther and farther out in the tail to get the required gap. And so as the number of anecdotes grows, the one that gets sent is more extreme. It's more biased. But whether that's a good or bad thing depends on the variance in the tail of the noise distribution. So if you have like a Gaussian noise, that's okay if, you know, if the sender had tons and tons of anecdotes, even ones out in the tail tell you a lot about the state. But if you have Laplace noise, the tail, it has a constant variance, and so you're in trouble. As you have more and more data, you get more and more polarized. Yes, exactly. So this is when there's so many senders. I mean, I haven't actually studied this in a networked model. That's kind of like what I want to do now, because what I'd like to say is that if the receiver has an additional strategic choice of which news source to listen to, they're going to drive towards polarization. So, if there's differing experience levels, then the receiver may prefer, like, they get higher utility from communicating with a less experienced sender who has more similar preferences, which is this form of polarization that she's just talking about. Great. So the third thing I'm going to skip, because I see I am at time. Yeah? Who's my chair? You're at 5 minutes? Okay. The third thing is about mechanism and information design. So, you know, we've now seen if the agent can think about taking decisions and can only use anecdotes, how do they do that? If they can communicate with each other only using anecdotes, what implications does that have for welfare and the polarization? And now what if I can design a mechanism using the anecdotes. And the mechanism that I have in mind is the one that a recommendation system might want to build. So you have a recommendation service like Yelp, who has a bunch of information about restaurants and wants to help short-lived agents, say tourists in New York who are short-lived for a variety of reasons, wants to help them figure out what restaurant to go to. And so classic work in economics and computer science has, this is the field of incentivized exploration, has suggested that you can cast this problem as a sort of multi-armed bandit scenario, and you can simply devise a Bayesian incentive compatible rule and just present, sort of using a revelation principle style argument, tell the agent what restaurant to go to, and they'll go there and be happy. But what I was interested in is, what if you need to present the agent with a set of anecdotes, and then they get to decide how to act? So we have a state of the world that's going to be, now this is now a multidimensional state. It's the quality of all of the restaurants in New York City, say Bernoulli with mean reward, mu A for restaurant A. And the anecdotes now are the reviews of past diners. I'll only use I'll assume that they're thumbs up, thumbs down, so +1, -1, and we're eliminating fake reviews. And the agents are going to come in at some time, step T, and they're going to select a restaurant based on the reviews that they see. And in keeping with this idea that agents just are sort of naively averaging anecdotes to take actions, I'm going to assume that the way they do that is they look at the empirical mean of the anecdotes that they see, and then they form some estimate, and I'll allow them to do some Bayesian updating if you like Bayesian agents or whatever. They're going to form some estimate somehow, mu hat, which gets closer and closer to the empirical mean as the number of reviews grows. So if you go to Yelp and you see a restaurant which has 1,000 reviews and 2 stars, you kind of assume it sucks, right? And if it has 1,000 reviews or like 2 reviews and 4 stars, you assume you don't know much about it. And so that's what this confidence bound is asking you to do. And when you form all of your estimates that are within, that satisfy this inequality, then you as an agent decide to go to the restaurant with the highest estimate. And the question I want to ask is, can the principal commit up front to a policy of which reviews to show agents? So the principal's power now is to pick a subset of reviews in a way that's going to minimize regret. And I'm pretty excited about this framing of this question, because I feel like there's many reasons that Yelp doesn't just tell us what restaurant to go to, right? They always present, all of these systems present subsets of reviews. That's in part because agents are heterogeneous. But really, I think it's because of some sort of transparency and data-driven actions on part of the agents. And so we need to think about which reviews should Yelp show people. And this paper derives 3 different policies that Yelp can leverage that get better and better regret as time goes on. And I'm talking to a crowd that's quite experienced with regret. So what I think is cool about this is that we're able to get agents that have their own incentives of how to act to get optimal regret when we can only present them with subsets of reviews. We're choosing this structure of the subsets of reviews before any agent walks in the door. So it's particularly interesting that we can do as well as adaptive policies. We can do t to the 1/2, even though we had to pick the review structure up front before the game even started as the principal. And so I think I will not have a chance to show you how we do that. But the sort of basic idea is that we can keep information contained in little information silos, so those agents are going to explore, and within the context of an information silo, because this half of the room only sees reviews from people in this half of the room, and that half of the room only sees reviews from people in that half of the room. And so we will explore, due to herding, maybe different parts of the space, right? And then after there's enough exploration, you can start to create layers of aggregators that see the exploration from both halves of the room. Say the rest of the university gets to see everyone in this room's review of the restaurants that they went to, and then they can leverage the exploration that was induced by the natural herding to get enough information to make accurate choices about the best restaurant. So that's kind of where I wanted to take you through this story of like, let's think about data as being fundamental to mechanisms and to economics, and see what happens as we build models in classic economic settings using data as its basis. And I guess, the sort of high-level takeaway here isn't really any of these individual papers, but more this idea that I'm excited about, which is that anecdotes, which are immutable facts that are correlated with the state of the world, form the basis of much of our economic and social interactions, and we should study models that use that as the foundational component. Thank you.
That was Nash equilibrium, wasn't it?
Perfect Bayesian equilibrium, yeah.
Yeah, it's not the Bayesian persuasion in the sense of Kamenika and Ganskor.
Correct.
So how would the results change if you were to look at it from that angle?
Yeah, great. So we do study that as well in the paper. If you are able to commit as the sender, all of this unraveling, this partial unraveling that you see in the results I presented goes away. And even if you have a different alignment, you can commit to sending the anecdote that's closest to your sender's posterior mean or theta. Yeah.
Which probably makes more sense. Which probably makes more sense in applications rather than the Nash equilibrium.
So like, I was trying to think about, say, newspapers which have a long history, maybe with editorial policies, maybe you think commitment is reasonable for them, whereas like politicians that get elected every 4 years, maybe commitment is less of a, it's always this question in Bayesian persuasion, like how much do you believe the commitment assumption?
Unless there's some other questions, regarding the first topic, there is a new trend in information theory, which is on age of information. So I'm not sure whether you're familiar with that age of information, where you throw away information which is kind of old and not useful. So I was wondering whether there is any connection between your memory restrictions and what to maintain there and the age of information research, which has been, well, the last 5 years or so that they have been.
I'm not familiar with this, but I would think that for information to get stale, you need the state of the world to drift. And so in my model, the state of the world is fixed, but if you let the state of the world drift, then I could imagine there being some relationship in the sense that you might even want to forget long-term memories more frequently because they might be unimportant to the current state. Yeah.
And that like you're looking at anecdotes from the perspective of how humans behave. Is there any sense in like doing experiments on real humans, especially in the first part of your talk, to see like what two things would they store?
It's really hard to elicit beliefs in experimental economics, but yeah, I've seen some sort of discussions of this in the psychology literature that I'm not sure it's not the sort of rigorous lab experiment that you might hope for. it would be interesting to think about how to set that up. It's hard to know what people keep in their head, right? Like, I think even like classic economics has trouble eliciting priors. So the question is if my assumption is that the sender has infinite memory in the communication game. The model, like the number of anecdotes that the sender has access to, N, is also common knowledge, and it suffices so long as the
Well, I mean, I was thinking if it was sort of in the paradigm of the first one, and I know I'm biased, I will only retain the stories that are anecdotes that are closer to my bias, and then what I'm going to tell the receiver is going to be different than if I was storing things in an unbiased manner.
Yeah, that's an interesting idea. Like, so basically the sender, I hadn't thought about it in that framing before. What I have thought about is if the sender can go out and like invest in getting more anecdotes, when is that a good idea, right? But like what you're saying is, what if there's just a process that generates anecdotes and the sender can only keep 2 of them in memory, which 2 are they going to keep? Mm-hmm. Yeah, that would change because they, like, in the first paper, you're just trying to get something close to the state of the world. In the second paper, you also want something biased enough to, like, help the guy unravel, yeah.
Do we have? I don't know if this question makes sense in the setting, but like in the first question, if you go away from single peak, what can we say?
Yeah, both. I'm heavily leveraging single peakedness in both the first and second setting, although that might not have been as obvious in the second setting. If you move away from that, you're going to have to, like, I don't know, maybe have some model of the world where you understand that there's, say, like 2 peaks, and you're like and you know that they're some particular distance apart, so you just need to go figure out this one. And yeah, I don't know how to analyze it, but I think it changes stuff.
But does that make sense in this context? Like,
you can ask the question. For
as
sure.
in, theoretically, yes, but like you have like
you have to think about where is noise coming from in the world. So I am pretty happy with single peaked noise. I think it's a common assumption in much of economics and econometrics and stuff. But like you could imagine worlds like settings where there's 2 peaks or something.